A force is real when it exists with respect to an outside non-accelerated observer, or inertial reference, that is, free of forces. In addition, since real forces are produced in pairs of equal and opposite components, Newton's third law must be obeyed. Therefore, we have the pair of equal and opposite forces, produced by a force provider, acting upon a pair of bodies, each for each force. The result is the opposite acceleration of the two bodies, with respect to the non-accelerated referential. A key aspect of the third law of motion is that it contains the second law. The third law, however, is the complete statement of all acceleration process requirements. The second law, as set out in Newton's Principia, allowed the mathematical development of the classical mechanics, since it contains the mass acted upon by an external force, and the resulting acceleration, related by the simple historical equation, force is equal to the mass multiplied by acceleration. Around 1750, D'Alembert outlined his principle, also known as the principle of dynamic equilibrium, joining the second law, with inertia as defined by Newton, in the Principia, definition 3. The issue of inertia as resistance to acceleration was raised by Kepler and Galileo, as a necessary property of mass, to control the acceleration rate of a body, of a given mass, acted upon by a corresponding force. As the analysis of the bases, established in the Principia, were carried out from 1750 onwards, an unnoticed problem emerged, with the unquestioned use of Newton's definition of inertia, as stated in the definition 3, in which inertia is defined as an innate force, that all bodies would manifest, when acted upon by an external force, disregarding his commentary attached to that definition. On that basis, D'Alembert set out his principle, in which a given body, acted upon by a force, manifests an equal and opposite force of inertia. A paradox, however, can be noted here, in which the force of inertia, despite being equal and opposite to the external applied force, does not prevent the body to be accelerated. In addition, the force of inertia has the problem of being a self-force, that a body manifests upon itself, while the external applied force is produced in accordance with the third law of motion. Therefore, the inertia as a self-force cannot be a real force. This problematic characteristic of the force of inertia also appears in the curvilinear motion. Based on Galileo's inference, later stated by Newton as the first law of motion, according to which all moving bodies tend to move in straight paths, it follows that a centripetal force must act upon a moving body, to cause the incurvation of its path. The moving body, then, would manifest upon itself a force of inertia, in this case a centrifugal force, equal and opposite, that is, outwards relative to the center of the curved path. Many people believe that doing so, this is the third law of motion, that is, the centrifugal force is the reaction to the centripetal force, but it is not. This misconception is, however, supported by the common situation of a driver in a car that moves in a curve. He feels a pull outwards, that seems to demonstrate the reality of the centrifugal force. A popular experiment to study the forces on the curvilinear motion comprises a body attached to one end of a cord, and a rotation center axis to the other. From the first law of motion, it is known that the moving ball tends to move on a straight path, defined by tangents to each point of the path. Since the curved path is contrary to its natural tendency, a force must act upon the ball, to incurve its path, the centripetal force. This is an accelerated motion, even with a constant speed, because the direction of the velocity vector is changing. And finally, the process is part of the third law of motion, since the experimenter is acting upon the ground, the surface of the earth, applying an equal and opposite force. For an observer attached to the ball, which is accelerated, however, the ball is not moving. He feels a pull outwards, for him equal and opposite to a force pointing towards the center of motion, that he identifies by the tension of the cord. He concludes that this outward force, a centrifugal force, is equal and opposite to the centripetal force, as required by the third law of motion. Many people believe, even today, that this is correct. But it is not. If a spring connects two portions of the cord, it can be clearly noted its stretching, caused by the centripetal force. One way to conclude that the centrifugal force is not real, is observing that, while the centripetal force has its source on the arm of the experimenter, and a reaction on the ground, the surface of the earth. The centrifugal force is a self-force the ball applies upon itself, which is impossible. It is the same kind of effort the Superman uses to fly, or move heavy objects. This is the nature of the force of inertia in the outdated D'Alembert's principle. A common example of this feeling is illustrated by a car accelerating on a straight road, relative to an outside floating non-accelerating observer. The driver is accelerating with the car, therefore, he is an accelerated observer. From the point of view of the driver, the car is not moving, with respect to each other. He feels, however, that his body is applying a rearward force upon the seat. It is easy to see that this force cannot exist, since the third law of motion, that is a condition for the production of forces and accelerations, cannot be applied. It is, however, the same kind of the self-produced force of the Superman, the force the body would produce by his own will. This is, again, the essence of the D'Alembert's principle. Under the action of an applied external force, a body resists and manifests, upon itself, a force of inertia equal and opposite. Even equal and opposite to the applied force, the force of inertia does not prevent the acceleration of the body, so it must be wrong. The confusion related to the inertia, as resistance to acceleration, as seen previously, came out, unfortunately, from the use, by Newton, of the term force of inertia in the definition 3. This term, added to the use, after Newton, of the second law of motion separated from the third law, as the base for the mathematical development of the classical mechanics, strengthened this misconception until around 1900, when the force of inertia was declared fictitious. Despite having used the term force of inertia, Newton was aware of how inertia, as an innate resistance to acceleration, is manifested by a body, in the context of the third law of motion. Instead of a force of inertia, a body would apply upon itself, however, it manifests an inertial resistance to acceleration, in the sense of an inertial drag. According to Newton's commentary to the definition 3, in the Principia, that resistance drag is manifested in the context of the third law of motion, therefore, will act upon the other body of the system as a force. In the commentary to the definition 3, Newton said, the inertia, is resistance, insofar as the body, for maintaining its present state, withstands the force impressed. And, it is impulse, insofar as the body, by not easily giving way to the impressed force of another, endeavors to change the state of that other. When the car is in an accelerated motion in a straight road, the driving wheels are performing as force providers, of a pair of equal and opposite forces, one upon the road, that is, the surface of the earth, and its counterpart upon the car. The driving force acts upon all parts of the car, including the driver's seat, this ultimately acting upon the driver's body. Since the driver's mass resists acceleration, the driving forward force acts upon the seat, which is then compressed due to the driver's resistance to acceleration. This enabled the driver's mass to be summed to the vehicle's mass. With this interpretation, the force of inertia, as a self-force, disappears, and the whole process can be seen as being in accordance with the laws of motion. Now let's consider the case of the car on a curve on the road. To simplify, let's suppose its speed is constant. Since the velocity is a vector, a change in its magnitude or direction is acceleration. If the magnitude is constant, when the car moves on the curve, the direction of its velocity vector is changing, which demands the action of a force, perpendicular to the velocity vector, the centripetal force. However, the driver feels a side force, from the center outwards, as seen from a distance by a floating non-accelerated observer. The driver feels this force like a centrifugal force, whose nature he cannot define, since he cannot apply the third law of motion. Therefore, this force is not real. In the same line of reasoning, let's suppose a ball is resting loose inside the car, on the left side. At the same time the driver feels a side force, the ball moves to the right. This reinforces the driver's assumption that an outward force is acting upon him and the ball. It has to be demonstrated that this is wrong, because Newton's third law cannot be applied. Another situation that leads to confusion is the motion of the car on the curve, considered from the point of view of an observer attached to the surface of the Earth considered fixed for this observer. This observer can see the car moving in the curve, and concludes that it is acted by a centripetal force. A ball loose on the left side of the car moves to the right with respect to the car. However, the observer notes that the ball is moving in a straight line, in accordance to Newton's first law. The observer can conclude that the ball is not acted by any centrifugal force. However, he is unable to explain the driver's feeling of an outward force, or engage in the popular misconception that a centrifugal force is acting upon the car, and the driver, in reaction to the centripetal force, in a tentative to apply the third law of motion, since the Earth is fixed, therefore not interacting with the car. Again, a wrong conclusion. This is a typical problem of a body rotating about a center O, acted by a centripetal force, against the natural tendency of the body to move on a straight path. Recalling the D'Alembert's principle, the body would manifest the supposed centrifugal force, not real but still popular. This is a wrong interpretation of the process, since acceleration is taking place, but the third law of motion, for rotation, cannot be applied. The correct explanation can be obtained only through the analysis being made with respect to a non-accelerated observer, floating outside the system under analysis, that is, not attached to the Earth or the car. This is the inertial observer, with respect to which the two bodies can be identified in inertial confrontation, and Newton's third law can be applied. Instead of a driving outward self-force of inertia, the body manifests an inertial resistance, in the sense of an inertial drag, when it is deviated from the straight path, tangent at each point of the path. Returning to the example of the car moving on a curve, and using Newton's commentary to the definition 3, in the Principia, the inertial resistance of the car to the incurvation of its path, is manifested upon the road, through its wheels, outwards, that becomes a force upon the Earth. The Earth resists inertially, and manifests this resistance upon the car, through its wheels, as the centripetal force. In this channel series, this has been called inertial confrontation, another name for the third law of motion. A brief summary can make this overview simple. On each point of its curved path, the mass of the car tends to move on a tangent, that is, a straight line. Since the car is moving on a curve, its inertial resistance to incurvation acts upon the Earth as a force, the centripetal resistance, while its centripetal force is acting upon the car. This centripetal force is the inertial resistance of the Earth. This tendency, of course, applies to the driver and passengers and loose objects inside the car. This dynamics is valid with respect to a non-accelerated observer, floating in space, not connected to the car or the Earth's surface. Taking 2 points of the curved path, it is observed the tangents to each point. Therefore, it is clearly noted that the curved path is an inward displacement away from the tangents, caused by the centripetal force, that is, the Earth's resistance. The inertial resistance of the car, and bodies inside, act upon the Earth as a centripetal resistance. The feeling of a pull outwards, when we move in a curve, therefore, is not a centrifugal force, but the inertial resistance to the incurvation of our path, that our bodies manifest against the pull inwards, caused by the centripetal force, in a dynamic mechanism fully explained by the third law of motion. This analysis showed that the motion on a curve is a sequence of displacements, from the tangent at each point of the path followed by the body, towards the center of the curve, caused by the centripetal force. At each deviation from the tangent, the centripetal acceleration, the rotating body resists, as a feeling of a pull outwards, and this resistance acts upon the body that is the source of the centripetal force, in this case the experimenter's arm, and, ultimately, the Earth's surface. The experimenter, supported by the Earth's resistance, produces a centripetal force, that sequentially, maintains the rotating body deviating inwards, away from the tangents at each point of the path. Now we can be aware that, when a car moves on a curve, a centripetal force is acting upon, as a result of the resistance of the surface of the Earth, that is, the road, against the natural tendency of the car, and the driver, to move on a straight line. The driver, and the car, manifest the inertial resistance against the incurvation of the path, that is, in acceleration, and this resistance acts upon the ground, as the centripetal resistance. The equal and opposite inertial resistance of the ground, the Earth's surface, provides the centripetal force on the car, through its wheels.